Hi, my name is Alexandra Patilio, and this is going to be a demo of the interacTABLE prototype working. So to start, I've 3D printed some modeling components. In black here, I have a 3D printed column. I've stuck an Arugo marker onto the bottom, which is going to be read by our processing sketch eventually. I've also printed a T-section beam here in white, as well as a beam marker. And the beam marker also has an Arugo marker stuck onto the end of it. So the components fit into one another like so, and I would just ensure that the beam marker fits onto the end of the beam. So I'm going to go ahead and model this on the table. Once we're satisfied with the configuration of modeling components on our table's surface, we can now go into Rhinoceros and start to digitize that model. So on the left here, you can see I've set up a Rhinoceros model where the plane will be coming in as blue, the columns coming in as black, and the beams coming in as white, just to mimic the real world scenario that I happen to have here on my table. So if we go and turn these on, you can see that right now this model is entirely empty. There's nothing there. On the right, I've opened up a grasshopper sketch. So what we're using right here is the UDP receive. UDP receive is a function of ghowl, which is just a plugin for Grasshopper. It allows you to send or receive data through UDP stream. So that's what we're using right here. I just want to draw your attention to this right here. So I have a folder called 3D files for importing. And this folder, if I go into the Rhinoceros properties, has been associated with this specific Rhino model. So it's going to be pulling from here for the 3D beams. You can see that I have a file called 8_beams. And I also have another file in columns called 11_columns. You'll see later why that's relevant, but this is the folder that the Rhino model pulls from when it's inserting STL models that I've previously modeled and then printed. UDP receiver is on and listening for an external message, but nothing is yet coming through. So we're gonna run this processing sketch. What we see here is a view from our bottom camera. So the first step in all of this is to calibrate our two cameras. Since there are two cameras that are communicating with one another, we have to just line up these crosshairs to then set the construction plane for both cameras. So I'm lining this up right now for the bottom camera. Now I'm going to save that, and we toggle back to our top camera, which is the connect. Again, I'm just calibrating the construction plane so that there's one set construction plane for the entire system. And once I have that in there and I'm satisfied with the crosshairs being lined up to those plane markers, I've now saved that. I can press P to now send the construction plane over to Rhino. So I've pressed P. If I go over to my Rhino model, you can see that something has come in, and that's a blue plane there. You can see over here a new message has come in. We now have a construction plane. Columns and beams are not yet in, but we'll toggle back over to our processing sketch and press the C key to enter column mode. So when we enter column mode, again, we get a view from the bottom camera. The bottom camera is looking up at the table surface, and it's reading marker number 11. So previously, I showed you a 3D columns folder that had in it saved 11_columns file. And so because this is marker number 11, it's going to look through that folder for column number 11. It's read that marker. I've now pressed C to send it over to Rhino. If I go over to our Rhino model, we both have one plane and a column that's been sent in there. Perfect. So I'm going to go back over to processing, press B to now enter beam mode. And so there is a little bit of noise happening just because of the black and white column to plane. We have an 8_beams file, and so that's what the system is going to pull from to insert that beam file. So I'm going to send that over just the same way I did, but I'm now pressing B. I've sent the beam file over. And if we go in here, we now have a beam, a column, and a plane in our Rhino model. Once we're satisfied with the Rhinoceros model that we've effectively communicated from the physical world into the digital world, we can go ahead and disable this UDP receiver since we no longer need it. We're now going to move into analysis. Analysis is right down here. The way that analysis is running is through Carumba. Carumba is a plugin for Grasshopper, which enables the finite element analysis of a Rhino model. This happens in 3 phases. The first phase is converting a design model into a construction model. So what does that mean? I'm going to go ahead and enable these. So once we have our 2 points in there, our 2 points have been set to the end points of that beam, the far left and the far right. So the way that Rhino speaks in terms such as lines and curves, those would be considered design terms. So Karamba requires us to speak in terms of construction terms. So you can see here we have a component that's called line to beam, and we're literally converting a line into a beam element so that we can eventually assemble it and then analyze it. So again, going back to this conversion between a design model and a construction model, what I've done here, I've divided this curve up into 20 segments. As you can see, those X markers there. The reason why I've done that is just so we eventually receive analysis at 20 incremental points as opposed to just the 2 end nodes. We've now fed a line into this line to beam, and we're ready to assemble our model. The assemble model component allows us to put in supports, loading situations, cross-section, and material selection. So all these things are considered user customization. So they'd be specific to your model and what you want to analyze. So for our purposes, we have a cantilevered beam. That's why I've set up the support as being only the first point here. You can see that if we did have a support on the end, it would drastically change the analysis. You can see it's all blue now, which is obviously a good thing. But I'm going to go ahead and disconnect that because that's not what we have. We have a cantilever. So this is a fixed support condition, which just means that you have translational and rotational support along all axes. Now for our loading scenario, I am currently using a uniform line load. You can use gravity, mesh load, pretension, any of these. It's acting along the Z axis at negative 27 newtons, but I can toggle with this since it's on a slider. You can see how the amount of load really affects the analysis. Now for cross-section, what I have here is this component is reading the cross-section of the 8_beam STL file. I can toggle with the height of that model. You can see as it gets larger or smaller, the analysis changes. What I have down here is the material selection. You can see when I'm using steel, that's the analysis there. It drastically changes if I move into concrete or wood. I'm going to stick with steel for now. So finally, we have our model assembled, and now we move into analysis. Analysis would be phase 2 of this whole process, so phase 2 of 3. Although it looks like just one simple component, it's actually the grunt work of this entire thing. We can feed this calculated model into model view and then beam view. So these 2 components here would be considered analysis interpretation, which is phase 3 of Karamba. This chart is something that we've pulled from the Building Code of Canada. It's a displacement chart. Basically, red indicates displacement of 50 millimeters or more. And so you can see that on the end here where we have support, we're basically in this zone here. And where we have no support, we're in a zone of concern. So in this panel, we have the color codes. We're sending 18 different color codes, and they're directly corresponding to displacement intervals. So what we have down here is our beam displacements, our actual beam displacements for the beam that we have, and the points at which they're acting. So all of this information is going over to processing. Processing is then sending it to the projector, which we'll see now. We now have our projector up there working to project a visual interpretation of our analysis results onto the physical model. And we've successfully overlaid digital information onto the physical world.